All right, folks. So, for a brief reminder, right, because it has been 3 days since we talked about this, okay, and also it's, relatively new / weird, okay, and there are some of you that weren't here on Friday also. So, we were talking about our new unit here. We jumped a chapter first of all, right? We went from chapter 8 to chapter 10, and that's because chapter 9 is a bit of a doozy, all right? Just not that you're interested, but like when I remember talking with Mr. Goff about potentially picking up ABVC to teach it and stuff like that, I was like, I feel pretty confident about the calculus, except for sequences and series, and that'll be our next chapter. All right, so. We'll see though, maybe it's just because, well, I don't know, maybe we'll see how it goes. But for right now, we're moving into parametric and polar, okay, and we're going to start with parametric first, and then we'll kind of get into polar as well, and then doing calculus with those two things. You may remember parametric and polar kind of like showing up later on in pre-calculus, right? And it's simple, but it's tricky because like we change kind of like how we perceive, I guess, or how we kind of like think about graphs and stuff, and so there's like similarities to what we normally do, right? But then with the change, it also brings, some level of discomfort. Changing things at such a basic level then kind of has a big effect on all the things that we do. But introducing parametric equations is basically introducing this thing called a parameter, a third variable that we use to help kind of relate things here, right? So we describe our x and our y variables now in terms of t, all right? So typically, right, we have x and y variables in terms of each other. That's rectangular coordinates, but now we introduce this parameter t, again, typically describing time. All right, typically it's using time, but it doesn't have to be describing time. And basically, these relationships then no longer tell us how x changes with y or how y changes with x. It says how x changes over time and how y changes over time. So we get both like an x and y position in regards to a certain time, okay? And so how do we graph these things? Well, much the same as you graph stuff in the past. You pick some t values in a table, you plug the t in for the x, or you plug t in here for the x relationship, get the x coordinate, and then plug that same t into the y equation here, get the matching y coordinate, plot the coordinates, okay? Even though there's 3 numbers there, we're only going to use the x and y coordinates in our xy plane, okay? But then how do we graph the t equals -2 part? Well, that's you just label the point, okay? And so then as we go here, t equals -1 is at 0, -1, t equals 0 is at -1, 1, so on and so forth, all right? With that labeling, then we also get this idea of like orientation or like kind of like a direction of motion here, right? As time goes on, we're moving along the curve in this direction, okay? So you can also kind of like have that way to think about it. All right. In this case, right, we're moving along this curve, and this is the curve over 4 seconds, right? What has elapsed? We've gone from time t equals -2 to time t equals 2, so that's 4 seconds. All right. We have then another curve right here. Again, we pick some points, graph it, and in this case, we're going from -4 to 4, right? And we notice, whoa, these are the same exact curves, okay? But one takes 4 seconds, one takes 8 seconds. Okay, so now we can introduce the idea of like speed as well, right? It takes longer in this relationship. You still kind of make the same path, right? But it's in a longer amount of time. So we can introduce the idea of speed and stuff like that too. Okay. Another thing we should be able to do, right, is eliminate the parameters. So that means you want to, rewrite things in terms of rectangular form. So that typically means solving one of these equations for t. Okay. In this case, we chose the x. And then plugging back into the other equation, so we got t equals 2x, and so then plug that 2x in for the t value right there, and so you can rewrite this in terms of x and y, eliminating the parameter. Okay, you eliminate the parameter that way. Here we did some of that rewriting. Here we did some rewriting, and we also graphed as well. Okay, so you get some circles and stuff, and again, more of that right here with that as well. All right, and so that brings us then up to this situation right here, okay, so the left field fence at Camden Yards is 337 feet from home plate and is 7 feet high. Chris Davis hits the baseball at a point 3 feet above the ground. It leaves the bat at an angle of 41 degrees and at a speed of 107 feet per second. All right, so we're given these relationships right here. So we have given x equals v sub 0 cosine theta t. And y equals h plus v sub 0 sine theta times t minus 16t squared. Okay? Now, according to this information we've got up here, right, we've got a lot of variables, but we can fill some of these in. So, for example, v sub 0, that typically means what, or represents what? Initial velocity or starting velocity, right? What is our initial or starting velocity here? 107 feet per second. Yeah, that's the initial velocity here. So that's v sub 0. Okay, so we have then x equals 107 cosine of theta. Typically represents an angle. Do we have an angle in this scenario, in this situation? 41 degrees, yeah, 41 degrees. Okay, and then that's all times t. So it's this quantity there times t. So in effect, it's really just a constant, a number, times t. Okay. So then y equals, you can fill in the same thing. Okay, h, we think probably represents a what? A height. Okay, bless you. What height are we going to use here?
3.
Yeah, the 3 feet, right? Okay, we're shooting, we want to, obviously with the ball, or Chris Davis wants the ball to go over the left field fence there, but we'll, yeah, right now the initial height there is 3. That's where the ball is struck. And the same initial velocity of 107, sine of 41 degrees times t, and then minus 16t squared. Okay. And of course, that's the effect due to gravity there. Bless you. Okay. So there's our parametric equations. That's all we had to do right there. Letter B then asks, how high is the baseball after 2 seconds in flight? So, what should we do with this? Or how can we go about doing this? How can we figure this out? So, Mike?
Plug 2 into the y.
Very good, right. So y is going to describe the height of the baseball. X is going to describe the, kind of like horizontal distance. Y will describe the vertical height there. Okay, and so, yep, we're going to plug 2 in. So we'll evaluate y at t equals 2. And so we get 3 plus 107 sine of 41 degrees times 2 minus 16 times 2 squared. Okay, so we'll type that in here. Sine 41 times 2 minus 16 times 4. Oops. All right, and we get negative 94.945.
Now you are
I'm in radians, and I need to be in degrees for this one. Whoopsies.
You can't be at a negative height.
Right, it wouldn't make sense, right? We're not playing like mole baseball or something.
Exactly. It's impractical.
Yeah, it just doesn't make sense. Okay, so 79.397 feet. Okay, of course, if you want to get just more decimal places, that's fine. And then you don't have to worry about rounding or anything like that. It'll just get cut off automatically for you there. All right, letter C. How long will it take for the baseball to reach its maximum height? How long will it take for the baseball to reach its maximum height? Okay, so we need to figure out what its maximum height is here. So let's see here. What did I? Yeah, okay. So this is a time, right? And we want to figure out the maximum height here. So I think we'll graph this and see right here. Okay, so let's graph this thing. So 107 cosine 41, and then 3 plus 107 sine 41, 16t squared. Oh my goodness, I have to adjust the window for that, of course. Okay. So some things here to keep in mind, right? So for our window, I'm going to make my t minimum be 0, okay? Because it doesn't really make sense to talk about, again, negative time, right? The ball hits the bat. The bat hits the ball at time t equals 0 there. And so I'm going to go up to like 10 seconds here, and we'll see. I put my t-step at 0.1. That just helps to kind of give you a lot of nice points and stuff like that. Now if we go and graph it here, we see we're clearly going to be off the scale because we're only going from negative 10 to 10 and negative 10 to 10 here. So we got to go way far out on the x max. So I'm going to do like, I think 337 feet from home plate. So I'll do like 350 for that. And then the y max, I don't know, let's make it 100. There's a c there. Ah, perfect. Okay. So there's roughly, let's see if I can even get further. Goodness, it looks like a good spread.
It's not a home run.
It's not a home run, you don't think? We'll find out.
Wait, did you grab both the equations?
Yes, both the equations there. Okay. What's the question?
What was your x maximum?
X maximum, sorry. So I just guessed it to be 360. I figured because if the fence itself is 337 feet from that home plate, then I just went a little bit beyond that, just to kind of get the full flight of the ball there, kind of thing, to get an idea at least.
Definitely a home run.
Okay, it's no, Mike said definitely a home run. Okay, and then just 100 feet high. I just guessed that. So, but there it is. Okay. And so then we can kind of trace along here and get an idea about where that maximum height kind of occurs. All right, looks like it's about 80 feet. Okay, there, about 80 feet. Okay. Like that. Okay. So about 80 feet is the maximum height, but of course we want the time there, so about time t equals 2.2 there. Okay.
Wait, can you show your calculator again?
Show the calculator? Yeah. Question gate.
Yeah, can you show like what you plug in to the?
Oh yeah. Okay. Let me go back to there. I just typed in the x and the y there for that. The x and the y there for that. Okay.
So is it like a good answer to write about like t equals 2 or do you need
So right, because this is an approximation at best, right? But perhaps we want to try and get more precise, right? So how might we try to figure out what the maximum height would be here? Actually, using calculus and stuff like that. So Kurt?
You would take the derivative of y, I guess, function and solve for when it equals to 0.
Okay, right. Find the critical point, right? Or find a critical point, find the other critical points, right? So we can tell by the look there it's going to be probably just one critical point. But yeah, so we'll do that here. So y prime, okay? And we're going to take the derivative here with respect to what? With respect to what variable? T, right? Because t is now our kind of like independent variable here. So the derivative of 3 is just 0. The derivative of 107 sine 41 degrees t. Do we need to use a product rule here? No, this is all a number, right? This all right here is a constant. So this is like literally like, 2 times t, right? What's the derivative of 2 times t? It's just 2. What's the derivative of 107 sine 41 times t? It's just 107 sine 41 degrees minus then 32t. Bless you. Okay. So now keep in mind here, we're not necessarily taking the derivative of the parametric equation itself. We're just taking the derivative of the y component right here. Okay, just that y component because we're only interested in when the ball reaches its maximum height. Okay, so anyway, so we'll set this equal to 0, as Kurt suggested there. Okay, and so you get t is exactly then 107 sine of 41 degrees all over 32. Oops, 32. There you go. Okay, which is approximately 2.193697378. Okay, seconds. So pretty close to our approximation there of 2.2. Again, there's no justification necessary here, so we can just say there's our answer. Okay. But you could show that to the left, right, the function would be, or the derivative would be positive. To the right, the function would be negative. The derivative would be negative, and show that it's increasing, decreasing. But there's no justification necessary here. We can just say it's that. Okay? So, questions on any? Oh, yeah, go ahead, Karen. So all we did here was just go, so we kind of ignore the x part, right? As far as maximum height, the x part of our parametric equation here is not going to determine height at all, right? It only determines the distance from the batter. This determines the height, and so we only take the derivative then of that height to see when it's equal to 0, because the idea, again, we want to find that maximum value. How do we find the maximum of something? You know, using that first derivative test. Take the derivative, set equal to 0, all that jazz. Okay? Is that good enough explanation for you there?
Yeah, that's fine.
Okay. So then letter D, all right, did Chris Davis hit a home run? Be sure to explain / justify your answer. Okay, so now we have kind of like, we have two parts we have to concern ourselves with did Chris Davis hit a home run? First of all, we have to understand, did the ball even make it out to 337 feet, right? And then if it made it out to 337 feet, what else we need to be concerned with? How high it was, right? Because it's got to be over 7 feet high in order to show that. All right? So, how should we go about trying to tackle making sure that these two things are so? What could we do here? Well, yeah, Karen.
We could find the time at which it crosses that length, and then we could find the height at that time.
Exactly right. Yep, so we'll just do that. Oh, question, Sean?
Wouldn't it be 4 feet? Like, wouldn't it be like 4 feet because he hits the ball at a point 3 feet over that?
So I see what you're saying, yes, but if you look here with the height, it takes into account the initial height of 3 there. So you're right though, depending on where we're like measuring from, but yes, we're including that 3 initial height, so it would be a full 7 feet high. So I'm glad you're thinking that way. But yeah, so Kara is exactly right. So we're going to first figure out at what time the ball reaches is a distance of 337 feet. So we'll then say 337 equals that 107 cosine of 41 degrees t. In other words, it's the time 337 over 107 cosine of 41 degrees. Okay. I would recommend against here doing this division and rounding at this point. Leave it the way it is. Okay. I know it's kind of yucky to rewrite or whatever, but if you round, you're going to get error and stuff like that. Okay, that creates error. So just keep that time. Okay, no intermediate rounding. All right, so then we'll take this time, and as Kara suggested, we'll plug it into the y, the height of our ball. So 3 plus 107 sine of 41 degrees times that 337 over 107 cosine 41 degrees minus 16 times 337 over 107 cosine 41 degrees squared. Okay. So there, we just plug that in. Now, when it comes to using our calculators for this, right, you can type this 337 divided by 107 cosine 41. Make sure you put parentheses around that denominator there. Oops, I'm off the screen. We do it this way. There we go. Okay, so. Okay, so we get that, right? And if you want to just be able to reuse this, right, if you aren't familiar with your calculator, right, you can use the stow button right there. So press stow, you get this little answer arrow, and that's going to take our answer, store it, and then you can type whatever thing you want in there. I'm going to use just the X button because I don't have to then, press any alpha keys. Oh, and I just messed it up there. Of course, I'm using T in this case because, well, that's what variable we're in, function, or parametric now, not function. But anyway, there's that. And so then I can just type in 3 plus 107 sine 41 t. And that t value that I stored that 4.17 in, that's what's going to be used there. Minus then 16 t squared. And then voila, 17.304. And this describes what? This number is describing what? The height of the baseball, right. So, does Chris Davis hit a home run? Yes. Yes. Okay. and we'll say something like, I don't know, Chris Davis does hit a home run because at the time the ball is 337 feet from home plate, it is 17.304 feet in the air. Okay, something like that. Okay. So, questions on any of that? All right. So that concludes kind of our introduction into reintroduction to parametric equations and stuff. And now we'll jump into the next page, which is calculus with parametric equations. We already kind of did a little bit right back there with taking the derivative of just the one component, but now we're going to do it for the entire parametric equation here. Okay. So let's take a look here, right? So the slope of the line tangent to a curve, we know that currently, right? The slope of a line tangent to a curve, we know that currently as dy over dx, right? That's what we normally used. But now the curve described by x equal to f of t and y equal to g of t, okay? It's also just the first derivative of y with respect to x, okay? However, right, in parametric, x and y are not in terms of each other, they're in terms of this other variable t, okay? So we have to kind of just do a slight adjustment for our derivative here, all right? Since dy and dx are both in terms of t, we're just going to, so if we want to find the first derivative of a parametric curve, it's literally just dy dt over dx over dt, okay? Or in maybe in simpler terms, y prime of t over x prime of t. So the first derivative of the curve, is the derivative of the y component over the derivative of the x component. Okay, like that. Okay. The parametric curve will have a horizontal tangent. So in the past, right, when we had horizontal tangents, what did we set equal to what? Or what was true? If we had a horizontal tangent in the past for rectangular coordinates, we would do, yeah, John. So not 0 over 0, just 0, right? Yeah, it'd be dy over dx equals 0, right? That was for that case. Well, now when we have dy dx and it's equal to dy dt over dx dt, which portion are we concerned about being equal to 0? Just the numerator, right? dy dt. So we only need to know when dy dt equals 0. And we want to be careful, right? Because we also don't want dx dt to equal 0 at the same time. Right, so as dy dt equals 0, good. We also don't want dx dt to be 0. And again, why don't we want dx dt to be 0? Then it'd be undefined, okay, or indeterminate, I guess, in that case, because you have 0 over 0. Okay. So then the parametric curve will have a vertical tangent. And again, that's when dy dx is undefined, right? In rectangular, but then for parametric, what's going to be true? Dx dt will be 0, exactly right. And again, we don't want simultaneously to that, we don't want the dy dt to be equal to 0. Because again, that would be an indeterminate kind of form there. Okay. All right, so let's try here. Letter A. So for the curve, x of t equals t cubed, y of t equals t squared minus 2t. So there's our parametric equation there. Find the equation of the tangent line to this curve at the ordered pair 8, 0. All right. So what do we need to write the equation of a tangent line? Slope and a point. Do we have any of those things right now? We got a point, right? We got 8, 0. So there's our point. Okay, right there. So we're like halfway done. We just got to find the slope. All right. How do you find the slope of a tangent line? What do we do? Okay, well, first we have to take the derivative, though, right? So we're going to take the derivative here. So dy over dx And again, I'm going to write this explicitly right now just because we just learned this. So, I mean, you guys eventually, you know, because it won't be notes, you'll be doing your own work. You can kind of skip steps here. I'm going to write dy dx. That's equal to dy over dt over dx over dt. Okay, which is equal to y prime of t over x prime of t. Again, I'm writing all this out, you know, maybe more than you really need to see. All right, but I'm just going to write it out because it's notes. All right. What is y prime of t? 2t minus 2. And then what is x prime of t? 3t squared. All right, and now we just need to plug in our point. So should I plug in 8 for t? Should I plug in 0 for t?
No.
No, because 8 is an x coordinate. 0 is a y coordinate. We need a t, a time. How can we figure out what t value to plug in here when we only have an x and a y value? What can we do? So yeah, Karen.
Did we combine the x and the y and make a parametric equation?
So yes, so you could rewrite these things, and then you could even have taken just like you could have like rewritten this in rectangular form, taken the derivative, and then plugged in the 8 and the 0 for that if you wanted to. That's one option. Okay. Yep, that's one option. Option 2, we could also find at what time we have an x coordinate of 8, or at what time we have a y coordinate of 0. So we can also use that. So let me show you that way here. Okay. So if we take that 8 and set it equal to our x parameter there of t cubed, we can cube root both sides and see that t is 2. Right? Or alternatively, if we chose to use 0 here, we could say, okay, 0 equals t squared minus 2t. Okay, we can factor a t. All right. And again, we see we get t equals 0 or t equals 2 from there. All right. We're going to throw out the t equals 0 because it's not kind of in agreement here, right? We want both of these to be the same time, and so we use the t equals 2. Okay. Both those to be in agreement here, so we use the t equals 2. All right. And so then we should evaluate the slope at what t value? 2. Right. So evaluate at t equals 2, which yields, let's see here, 4 minus 2 is 2. 2 squared is 4 times 3 is 12. 2 twelfths or 1/6. Okay. And again, we already have that point, the xy coordinate of 8, 0. And so we can write y minus 0 equals m times x minus 8. Or you could just say y equals 1/6 times the other quantity x minus 8 there, but I'll make things more difficult. Question? How do we get 2 right here? So the idea is, right, that this is our point. It is at this time, or this, not this time, at this location that we want to find that tangent line equation, right, 8, 0. But there is a time that arrived that has us, you know, there is a time when we are at this location now because we're talking about parametric. And so we just use this 8x coordinate, put it right here, set it equal to the t cubed. And now then allows us to solve for the time at which we are at the position when x is 8. And then we use that time to then plug into the derivative there and stuff.
And then what you do is, once you plug 0 into the y, you definitely confirm that. Like,
Just kind of confirm it, or just show that you could do it, you know, with either one, you know, kind of thing. Use either one.
Need 1 to be true for you to be able to use it.
You only really need to check one here, but you do want to be careful. I mean, let me say it this way. Maybe it's good that we checked both here because let's say you maybe chose to do it this way, right? You end up with 2 answers here, but here it's only just the one. It's time 2, and so you want to make sure, I guess, it matches for both. So the time should be true for make it true for both things.
Okay.
So yeah, I would say you want to check both. Okay, so yeah, do check both there just to make sure that they do end up being the same time value, or you want the same time value, right? Because it's got to be simultaneous. Okay, so why don't you guys go ahead and try this one? Find the points of the horizontal and vertical tangents to the curve. All right, so go ahead and do that. All right. So remember, the horizontal would be when the slope equals 0, or in other words, what part of our parametric derivative here do we need to be equal to 0? Just the numerator, right? So dy dt equals 0. And then for, of course, vertical, okay, that's going to be the slope is undefined. Okay, so in other words, that would be dx dt equals 0. Okay. Here we go. Ah, I see some people right still. I'll give you like a few seconds, maybe not. Yes. All right. All right, so let's take a look here. So, Cassie, your number's up. dy dt. What is dy dt in this situation?
2t minus 2.
What is dy dt?
Are you asking me?
Yeah, you. Mhm.
Oh.
Please. Sorry, your number came up here. That's why I said that.
Um,
So here's y, right? T squared minus 2t. So what would be dy dt? What's the derivative of that?
2t minus 2.
2t minus 2. Right, and that's equal to 0. All right, we'll solve for t here. So we're going to add 2 over, divide by 2, we get t equals 1. Very good. Okay. Is that our final answer, though? What do you say?
No.
Is that right? Where it says find the points. So that means we need to come up with an x coordinate and a y coordinate. Well, what do we know? Well, x of t is t cubed. So if we want to find the x coordinate, what should we plug in here for t? 1, right? So it's just going to be x of 1, comma, y of 1. Then for the other one, that's going to be our coordinate there, which is going to be then 1, comma, and let's see here. 1 squared is 1, minus 2 will be negative 1. So our final answer here should be the point 1, negative 1. Okay? Yes, we use t to find the time at which this occurs, where you need to find the actual coordinate there. Okay? Thank you, Cassie. Nick, how about the second one here, the vertical? So at what time are we undefined here?
T equals 0.
Okay, right, because we're going to set the 0 equal to 3t squared. That is, again, the bottom of our derivative there, right? Okay, so the derivative of x, or x prime of t, is 3t squared equal to 0, so t equals 0. Okay, and so then what is our position at that time 0, Nick?
0, 0.
0, 0 as well. Yep, x of 0, y of 0 is 0, 0. Okay, again, that's just you plug in the 0 there. 0 cubed is 0. 0 squared minus 2 times 0 is also 0. So you get 0, 0. All right, questions on any of that? All good? All right, so now we're going to take a look at the second derivative.
Oh my god.
Oh my god. All right. So this is like a little bit more complicated. Well, it looks a little more complicated, but it's just because of, again, the kind of the nature of what it means to take the second derivative. So if you remember, right, back when we learned to take the first derivative originally, okay, in rectangular coordinates. So let's back up a step here, just kind of refresh our memory about what it means, right? If we started with something like the first derivative, typically we wrote that as like dy dx, right? The second derivative would be then taking the derivative of that. Okay? We take the derivative again of that, and that would yield d squared y over dx squared. Okay? And that would be the derivative with respect to x, or the second derivative with respect to x. Okay? So we took the derivative of dy dx with respect to x, right? Okay. Well, we can take that second derivative idea, okay, and then rewrite that exact idea. Again, in rectangular coordinates, isn't this the same thing, right? D squared y over dx squared, that is the second derivative. Or the other way of writing that is derivative of dy dx with respect to x, right? It's the same thing. But then what do we know, right? Well, we need to be in terms of t here because of the parametric equation. And so d becomes d over dt over dx over dt. We just make these things with respect to x, right? These would simplify back to this, right? D over dt over dx over dt would simplify back to this. Okay, you can imagine multiplying the top and bottom by like dt, which is really multiplying by 1, dt, and then dt here would be multiplying by 1, but the dt's would then cancel. Okay, so we can go back from here to here if we wanted to. But again, we're trying to rewrite things in terms of respect to t and stuff like that. All right, so then we've got that in terms of t. And we also can rewrite dy dx in terms of t, right? What is the derivative of y with respect to x in parametric? Well, we just did that back here, right? Dy dx was dy dt over dx dt. And so that's what we're going to do as well. Okay? So we're going to keep the d over dt and the dx over dt here. And we'll rewrite dy dx as dy over dt over dx over dt, like that. Okay. Oh, actually, I think I skipped a step here. Hang on. My apologies. This should be... Never mind. I'm making this hard. Let me go back. Right here. We'll go down from there to there. Okay? I'm making this harder than it needs to be. D over dt, dy over dx over dx over dt. That's all I need to show.
Just as hard.
It's just as hard. All right. So actually, yeah, this makes it easier. Okay. So sorry about that. Let me zoom out on that just to make sure we get that okay. Okay. So all I did here was just move that dy dx up into the numerator, left the dx dt in the denominator. Okay. So what is our second derivative? It is just the derivative with respect to t of that original first derivative. Okay. Typically, then, this is going to involve a quotient rule. Okay. Typically involves a quotient rule there. Whoops, get off that. And then all over, then, the derivative of x with respect to t. Okay? So the only thing, when we go to take that second derivative, or we go to evaluate that second derivative of our parametric curve, the only thing that we end up really taking the derivative of once again, well, we just take the derivative of our first derivative here with respect to t, and then put it all over the derivative of x with respect to t. And that's all there. That's what there is to it. Okay. So again, it's the derivative of the first derivative with respect to t over the derivative of just that original parametric relationship x with respect to t. Okay. Sorry. That's the quotient rule there. Okay. And that's again just moving that dy dx up into the numerator there, d dt of the dy over dx over the dx dt. All right. So let's take a look at that here. All right. So we're going to look at the parametric equation given as such. Letter A is pretty straightforward, though. We're just asked to find dx dt, dy dt, and then dy dx at the time t equals 1.6, and then explain kind of like the graphical meaning of each things at that time 1.6. Okay. So dx dt, that's easy enough. We've got x equal to 3 plus sine pi t, and so then dx over dt is just the derivative of this thing, right? So the derivative of 3 will be 0. Derivative of sine of pi t, well, this time that t is inside the sine, like that. Okay? And so what's the derivative of the sine of something? Cosine of pi t times the derivative of what's inside, so times pi, right? Or we could really just say pi cosine pi t, like so. Okay? Let's just keep taking the derivatives here. So what's dy dt going to be? Well, the derivative of 1 is, 0, and then, derivative of e to the 2t will be 2e to the 2t, like that. Okay? And then the dy dx, right, which is the first derivative, remember that is y prime of t over x prime of t, okay, which in this case will be then 2e to the 2t, right, from that dy dt, and then dx dt, which is pi cosine pi t. Okay, just like that. So we found the 3 things we wanted to find, and now we're going to evaluate them at t equals 1.6. So evaluate at t equals 1.6, evaluate at t equals 1.6, evaluate at t equals 1.6. Okay. And then how are we going to evaluate these at t equals 1.6? Calculator. We got to use our calculators for this. Okay, so make sure we're back now in radian mode, first of all, if you're out of that.
Oh.
Okay, so, okay, times 1.6. And so when you do pi cosine pi times 1.6, you get approximately 0.97080555194.
Make sure we're in what?
Radian mode now, because we're evaluating it with pi's and stuff like that, so we're going to assume that's in radian mode. Okay. Oops. All right, and then 2e to the 2 times 1.6, or 2e to the 3.2 there is approximately 49.065060039. And then, of course, 2e to the 2t over pi is just going to be these divided, right? And we get about 50.5405657. Okay, and so our next task here, and this is going to be not like, super long, it's just like then explain the graphical meaning of each. So, dx dt, right, that is a change in x over a change in time. Okay, so this is a positive 0.9708055194. It's positive, and x is in charge of kind of our left-right. Right? How we're moving left to the right, right? So since this is a positive 0.9708, we can say that this means that our object, or we are, our thing here is doing what? Moving to the right, yeah. Okay. Because our rate of change of that horizontal motion, the rate of change of the horizontal motion is positive, so that indicates a moving motion to the right. Okay, if it was negative, we would expect our horizontal motion would be to the left, right? Okay. Now for the next one, dy dt, of course, now we're changing not from horizontal, that's our vertical motion. It's a positive value as well, so that means we should expect it would be moving which way? Up. Yeah, moving up. At that instant. And then 50.540, also positive, right? But now we're just talking about dy dx. And so we normally use dy dx to describe the slope. Yeah, the tangent slope. So the slope is, about 50.5406. Okay? And then that's the best we can say right there with that. Okay? Since the slope is positive here, that either indicates one of two things. Right? It indicates one of two things. Either dy dt and dx dt are both positive, or what? They're both negative, right? So that means dy dt and dx dt are both the same sign if you have a positive slope, right? Because how do you find the slope? You take dy dt and divide it by dx dt. So if you have a positive slope, that means one is positive and the other is positive. Or if one is negative, the other is negative. Okay? So they're both moving. It's either moving left and moving down, or moving right and moving up. Okay? You won't have opposite kind of directions there. Okay? So now let's take a look here. Determine if the equation is increasing or decreasing. Okay? And then concave up or down at t equals 1.6. Okay, well, we can already answer one of these questions, right? The equation is going to be what at time t equals 1.6? Increasing or decreasing? Increasing, and that's because what? Because dy dx is greater than 0, or the slope is positive there. Exactly right. So since we just calculated that, so I'll just say since dy dx is greater than 0, okay, at t equals 1.6, the curve is increasing. Okay. To determine concavity, concave up or concave down, what do we need to observe or analyze? Second derivative, so f prime prime, right? Or d squared y over dx squared, right? So we'll evaluate that. We'll go back up here to what we said, right? That second derivative would be. So the second derivative ends up being the derivative with respect to t of the first derivative over dx dt. Okay? So I'll write that right here. D squared y over dx squared equals d dt of dy over dx over dx over dt. Okay. We know what dy dx is already. Oh, I guess I could also, well, oh, whatever. I'll substitute in a little bit at a time here. So dy dx is 2e to the 2t over pi cosine of pi t. Okay. And this is what I was kind of showing earlier that I just decided to skip, but there's dy dt, there's dx dt. That's what I was showing. I mean, you can't even see it now, but I had dy dt over dx dt there, but it was just going to be too much writing, so I just did it this way. But there's your d. So you could also think of it instead of dy dx, you could say dy dt over dx dt because that is what dy dx is there. Okay. Of course, I can also substitute in what is dx dt here, right? We know what that is. What is dx dt? Yeah, pi cosine pi t. So ultimately here, this is what we want to evaluate. The derivative with respect to t of 2e to the 2t over pi cosine of pi t all over pi cosine of pi t. So let me pause right here and just make sure we're all good to go. So any questions up to this point? This is our, right here is where we want to make sure we're okay with, up to this point. So any questions up to this point? All right. So what work is there still left for us to do here? What do we still have to do? Take the derivative, okay, of that numerator there, okay, with respect to t, right? And these are already in terms of t, so that's great. And in order to take the derivative of this, we have to use the what? Quotient rule. And so this is going to be a quotient rule all over pi cosine pi t. Great. All right. So quotient rule, right? Bottom times the derivative of the top. Well, thankfully, 2e to the 2t is easy. It's 4e to the 2t. Minus the top, 2e to the 2t, times the derivative of the bottom. Derivative of cosine, negative sine. So it's going to be negative pi sine of pi t times the derivative of what's inside. So we're going to have another pi here. So I'll just go ahead and make this negative pi squared. Okay? And that's all over the bottom squared, pi cosine pi t, quantity squared, and that's all over pi cosine pi t. It's great.
Looks good.
So good. All right. Now we can do a little bit of simplification here, right? So for example, the negative pi squared, we can bring that out with the minus here and make this then plus a positive there. Okay, so then it's just plus now there. Also, instead of dividing this whole fraction, instead of dividing it by pi cosine pi t, we can instead multiply by 1 over pi cosine pi t, right? Dividing by something, dividing by pi cosine pi t is the same thing as multiplying by its reciprocal, 1 over pi cosine pi t. And what do we notice here? They're the same. And so we can make that then, let me go ahead and simplify some of this in here. So let's see, it'll be 4 pi e to the 2t cosine pi t. Let's see here, that'll be then plus 2 pi squared e to the 2t sine pi t all over pi cosine pi t quantity cubed. Okay, And we're not quite done yet, because now what do we have to do? Plug in 1.6. Yeah, evaluate at t equals 1.6. Okay, exactly. Okay, so let's see here. So again, you have a couple, ways you want to do this. If you want to do it in chunks, you can, but just be careful about that intermediate rounding. Try and give as many decimal places as you can. Another option here is, since we're going to make 1.6, so again, I'll do 1.6, store that in for t, and then I'll just go about writing this out. So 4 pi e to the 2t cosine pi t plus 2 pi squared e to the 2t sine pi t. Okay. Now, since I didn't put parentheses around my numerator, I guess I should do that. So I'll go back and fix that here. So insert parentheses around my numerator. Divide that by parenthesis pi cosine pi t to the third. Okay. So I get something like that. Oh. Okay. Feel like pi cosine pi t cubed 4 pi e to the 2t cosine pi t plus 2 pi squared e to the 2t, sine of pi t, yep, okay, all over pi cosine pi t cubed. All right, so again, I got that. You guys didn't get that? Did I type something? Let me see here. What did I get? Negative 399? Okay, so now I'm wondering what I typed in incorrectly here. Let's see. Yeah, I think it should be negative 399, so let's see here. So 4 pi e to the 2t cosine pi t plus 2 pi squared e to the 2t sine pi t pi cosine pi t to the third.
You're not cubing the whole thing, you're just cubing the...
Oh, thank you. Yep, I see it now. I forgot the other parenthesis there. There it is. Negative 399.242. Woohoo! I got the right answer. Yay! All right. So regardless, right, or ultimately here, what does this tell us then? It's less than 0, and so right, the curve is concave down at t equals 1.6. Okay. Huzzah. Moving on. Questions on any of that? Oh, yes, Karen.
How do you store
T in the calculator? So, yep, stow button. I'm using T's. The reason why I have T's is because my mode is currently set to parametric. If you were in function mode, you could store it in X instead and then go from there. But yeah, so I did 1.6, hit the STO button right there, okay, just above the on button. And that gives you a little arrow, and then you type in the variable t. I just normally use whatever, this button right here. You could use any of the alpha. You could use alpha A, alpha B, whatever you want to do there. I used to use the variable, and so now it's 1.6. The nice thing also about that, Kara, is like when you go to like graph things, and you use t, and like your y equals and stuff like that, this t is now just the generic t. It won't use that 1.6. It only uses 1.6 on the home screen there. So, all right, moving on. So, find the first two derivatives of the function, thank you, determined by x equals 5 cosine theta, y equals 4 sine theta minus 3 at theta equals pi over 6. And then find if the curve is getting closer or further away from the x-axis and y-axis at this point. Okay, so why don't you guys go ahead, find the first two derivatives, okay, and then we'll, if you want to, kind of ponder those two questions, we'll do that as well. So go ahead and take a few minutes, answer and at least find the first two derivatives, okay, and then think about whether we know if the curve is getting closer or further away from the x and the y-axis at that time, at that point. Okay. Soon. So find the first derivative, find dy dx, which you know is dy dt over dx dt. Then find the second derivative, d squared y over dx squared, which is, the derivative of dy dx with respect to time over dx dt. Okay? Or I should say dy d theta dx d theta for this case, right? Because we're talking about theta as our parameter.
Because I don't remember the derivative of cosine, so that's a good.
Negative sign.
Looks. Yeah.
Mike.
It's been a while, right?
Oh, I'm still in this class right now.
Your first derivative you should be able to rewrite as a single trig function. Okay.
Oh, I see. I'm not gonna do it.
That'd be a pain. I'm not trying to do that. Never see you again.
more seconds here and then we'll reveal. We are going to do arc length, and we are going to talk about example 4. Okay, so we're going to get up through example 4 here. So, got it close, but we should be fine. Okay. All right. So I went ahead and also evaluated the derivatives at that theta equals pi over 6, because that's what we also ultimately want to be able to do. All right. So again, I went ahead and found dy d theta, 4 sine theta minus 3, right? The derivative of that would be 4 cosine theta. Derivative of sine is cosine. Dx dt, derivative of cosine, negative sine, so negative 5 sine theta. And then, of course, dy dx, what is that? That is dy d theta over, dx d theta. And so it's 4 cosine theta over negative 5 sine theta, which we can put those together. All right, that's why I was trying to help you out there with a hint. Cosine over sine is just cotangent, right? So it's negative 4/5 cotangent theta. Evaluate that at pi over 6. If you're uncomfortable, right, about evaluating cotangent at pi over 6, remember your reference triangles here. Cotangent, well, it's the reciprocal of tangent. Tangent is opposite 1 over adjacent root 3. So then cotangent of pi over 6 would be root 3 over 1. So it's just negative 4 root 3 over 5. Okay? What does that then tell us about our curve here? If dy dx is negative, that means what is true? The graph is what?
Moving to the left.
Well, we want to be careful here, right? The graph is not necessarily moving to the left. This is dy dx. It's just decreasing. Just decreasing, okay? So, the curve, I'm running out of space here, is decreasing. Okay? At theta equals pi over 6. Okay? Because it's less than 0. And then for our second derivative, remember that is the derivative of the first derivative with respect to theta, bless you, over dx d theta. Okay. And so we get 4/5 cosecant squared theta over negative 5 sine theta, but dividing by sine theta is the same thing as multiplying by 1 over sine of theta. But what is 1 over sine theta? 1 over sine theta is another cosecant of theta. So you get cosecant cubed of theta, and then the 4/5 divided by negative 5 is negative 4/25. Evaluate at pi over 6, you get negative 32 over 25. Again, if you're cosecant, right, if that's uncomfortable for you, using that reference triangle, right, cosecant is 1 over the sine. So if sine of pi over 6 is 1 over 2, cosecant will be 2 over 1. So 2 over 1 cubed, so 8 times negative 4, negative 32 over 25 there. Okay, and this indicates what about our graph? Concave down, okay? So the curve is concave down at theta equals pi over 6. Okay, so question here?
Did you use the quotient rule or the dy over dx?
So in this case, it wasn't necessary because you could have used the quotient rule if this was your original derivative there, yes, okay? But because I was able to simplify this, I was actually able to avoid using the quotient rule there and just did the cotangent. Took the derivative of cotangent. Derivative of cotangent is negative cosecant squared. It's positive though because it was negative cotangent, so the derivative of negative cotangent would be positive than cosecant squared theta. So that's all we had to do. That's all we had to do. Okay. So do try and simplify that first derivative, of course, right? Just like normal. Simplify that first derivative to help you then take the second derivative. Okay? Or take the derivative again. Now, how can we determine though if our curve is getting closer or further away from the x and also the y-axis at this point? So what will help us determine, let's just start with getting closer to the x-axis. So if we're getting closer to the x-axis or getting further away from the x-axis, that's like a vertical motion, right? Because the x-axis, right, that's right here. If we're getting close to the x-axis, that means we're moving in towards it vertically, okay? Or if we're getting further away from the x-axis, that means we're moving away from it vertically. And so to determine if we're getting closer or further away from the x-axis, we need to look at
The y's.
dy d theta, okay? How is dy d theta changing? And we want to specifically evaluate dy d theta at what value? Well, it's saying at this point. So yeah, theta equals pi over 6. So you plug pi over 6 into dy d theta, which is going to be, 4 cosine pi over 6. Okay. Cosine pi over 6, root 3 over 2. So we'll have 4 root 3 over 2, or just 2 root 3. Okay. What does that 2 root 3 then indicate about the motion of our curve here?
It's going up.
So it is going up. Exactly right. Okay, it's positive, so it's going up. Is that enough information to tell us whether we're getting closer or further away from the x-axis? Yeah, no, it's not, is it? Because if we're below the x-axis, going up means we're going closer to the x-axis. But if we're above the x-axis, going up means we're going further away from the x-axis. How can we determine where we are? So right, we're going to plug pi over 6 also into the original parametric relationship here. And I'm just going to do it for both, if you'll just kind of allow me here. So we'll say x of pi over 6, comma, y of pi over 6. Let's just take care of this both simultaneously here. Okay. So again, cosine pi over 6 is going to be root 3 over 2 times 5. So this is going to be 5 root 3 over 2 for the x value there. Okay. And then sine of pi over 6, 1/2 times 4 is 2, minus 3 is negative 1. So I get the point 5 root 3 over 2, comma negative 1. So what quadrant will we be in with this information? Fourth quadrant, right? Somewhere like right here, we'll say. So now with this information, armed with this information, the fact that we are moving up from this point, are we getting closer or further away from the x-axis? We're getting closer, right? Okay, so closer to x-axis. All right, and then to determine if we're moving closer or further away from the y-axis, we're going to have to look at what? The left-right motion, so dx dt here. Okay, and again, evaluate that at theta equals pi over 6. Okay, so we'll plug that pi over 6 into dx dt. Sine of pi over 6 is 1/2, so we get negative 5/2. Okay, which is less than 0. Okay, so for dx dt being less than 0, that means we're moving which direction?
Left.
To the left. Are we moving closer or further away from the y-axis? Closer, because we're right of the y-axis and we're moving to the left, and so we're getting closer. Okay, just like that. Oof, I'm really running out of time. All right, let's scoot on down here to, any questions on that before I move on? I want to get to this last formula here. Okay, arc length and parametric, right? You may remember arc length in the rectangular, whoops. As being the integral from a to b of the square root of, if you remember we said it, we started out as being dx squared plus dy over dx squared, and then dx like that, but then we just made it 1 because the dx is over dx over dx is just equal to 1. So it was 1 plus dy dx squared, square root of the quantity, 1 plus dy dx squared dx. Well, arc length of parametric is, again, the integral from a to b of the square root, but now we're not taking the derivative with respect to x anymore, we're taking the derivative with respect to what? So it's going to be dx dt squared plus dy over dt squared, and then we're going to integrate with respect to dt, right? Exactly, with respect to t. Okay? So turn the page here real quick, and I'll just get this last one set up for you, all right, and then we'll finish it off tomorrow. Oh, I'm sorry. My apologies there.
Are you collecting problem sets today?
I might run out of time, but I would like to. But we'll probably get them tomorrow just because we're not going to have enough time, I think, here. Okay?
There's no time.
So, there is time, okay? for the arc length here, all right, you got it down okay? Okay, good? Okay. So then length, okay, remember is the integral from a to b, square root dx over dt squared plus dy over dt squared, square root of that, dt. There's our x, there's our y, so I'm out of time. Well, you see it. Just take the derivative of this with respect to t, plug it in there. Take the derivative of this with respect to t, plug it in there. Okay? Quantity squared, and so on and so forth. This one you can actually do without a calculator. Okay? You can simplify it down. We'll see it tomorrow, though. Okay? We'll finish it up. Okay? So, I'm sorry, yes. And homework is also posted to Google Classroom as well.
Like the whole first page.
The whole first page, my bad. Yeah.
Thank you.
Homework right there.
I have a problem.
Oh, you put the problem set in there too? Okay, yeah, you can put it right there. I'll take care of it. Any set requests for today? Any set requests? Ariana? Madison, Julia? Never mind, don't come in. Okay, Madison, no for you still then? Okay, Ariana, yes? Yes. Okay.
I might have a meeting with Miss Southern that has been planned for like 2 weeks. So
Okay,
just got back today.
I'll put you in. Any other set requests? All right. Homework. You just put it on my keyboard there. I'll take care of it. Thank you. Homework. I'll take it. Thank you.
My book bag. I'll give it to you then in a minute.
Okay, that's fine. We'll see you then.
Do you think our board is gonna clear up with the
The homework. Go ahead.
And then I just had to start writing notes. And
I understand. I mean the So you just say you just feel uncomfortable about arc length. Is that what you're feeling? Okay.